The more that we become dependent on electricity for service, the more outages become more risky. So one of the things that people become concerned about are long duration outages, which last roughly 72 hours or more. One way to protect against these high wind, high dry climate events, and particularly reduce wildfires, is what they call power safety shutoffs in California, where they would actually shut off power to a large section of the grid. Now that that is happening more frequently, right, people are concerned about what happens when they go without power. A way to combat this and to allow people to have safety and security in the amount of electricity that is being supplied to them is to install backup power generation at different parts of the distribution network. So that is what one of my students, Arnav, has been looking into. He has been working on tying two optimization models together. The first is going to be looking at what power sources should we be using to power different parts of the distribution network. And the second is going to say, okay, now that we have said that we're going to build a certain number of power plants and power plant types in a certain part of the distribution network, then we want to run it through what we call an AC power flow model. So that's going to actually look at the flow of current and electrons across the network to say, is it actually feasible?
When we tested our methods on a real-world feeder based in California, we found that hybrid energy systems would be able to effectively provide backup power at different levels of decentralization. These hybrid energy systems could be located at 1, 2, or 3 different locations on the grid and still provide backup power effectively to the local energy consumers. Now, increasing the decentralization of these solutions increases the amount of power needed by 1 or 2%, but increases the amount of capacity of the different technologies by as much as 15 to 30%. These hybrid energy systems can provide electricity effectively to local energy consumers, as much as 90% of their needs throughout the year.
So, along with our colleagues at the Colorado School of Mines and at the University of Vermont, my student Arnav has first built out an optimization model that looks at the distribution network. This is going to track the flow of electrons between the different poles and wires around a residential area. And then we've also tied that with a model that was started at Colorado School of Mines, which looks at, okay, if we want to meet a certain amount of electricity supply to a region, what types of power plants or smaller generation facilities like solar panels, fuel cells, or storage should we deploy in the region to make sure that we can cover all of people's refrigeration, all of their cooling and heating, all of their medical devices. So then he's been working on tying those two optimization models together to better understand how the flow of electrons needs to be across the distribution network, particularly during long duration outages.